Welcome. Let's solve Leetcode 2429, minimize XOR. Given two positive integers, num1 and num2, find the positive integer x such that x has the same number of set bits as num2 and the value x XORed with num1 is minimal. Note that exclusive OR is the bitwise XOR operation. Return the integer x. The test cases are generated such that x is uniquely determined. The number of set bits of an integer is the number of ones in its binary representation. Okay, let's go over example 1 here. The binary representations of num1 and num2 are 0011 and 0101 respectively. The integer x has the same number of set bits as number 2. And the value 3 XORed with 3 equals 0 is minimal. So that's why the return value is 3 here. Okay, example 2. Number 1 is 1, number 2 is 12. The binary representations of num1 and num2 are 0001 and 1100 respectively. The integer 3 has the same number of set bits as number 2, and the value 3 XORed with 1 equals 2 is minimal. Okay, so let's get started. Let me push this off to the side. All right. Sadly, I already recorded. Sorry, I made the video, but I didn't press the record button. So we'll just use the notes from last time. All right, so let's suppose that B has 5 set bits. And remember, our overall goal is to find a value x such that x exclusive ORed with A is minimal. Suppose B has 5 set bits. It doesn't really matter what the value of B is. We just care about the number of set bits for B. Now, suppose A is this. Now, for those of us who are not familiar with XOR, it's whenever you have something that, so for example, 1 XORed with 1 is 0, meaning exclusive OR means one or the other at most has to be set. So when they're the same, it's 0. So same thing for 0, 0. 0 XORed with 0 is also 0. However, when we have 1, sorry, this is 0. But in this case, this would be 1 here. 1 XORed with 0 is 1, and 0 XORed with 1 equals 1. Okay, so that's just a quick refresher for those of us who are unfamiliar with the XOR operator, or exclusive OR. So what we can do is, if we want A XORed with some value to be minimal, well, we know that if x and A are equal, we know this, if A and x are equal, when we XOR them, it's going to be 0. So we know that. Now suppose, so here A has 4 bit sets, and we know B has 5 set bits, according to my example. That means we need one more set bit. So the question is, where do we add that one more bit? So in binary, the more significant digits are to the left, and the least significant digits are to the right. So if we have to turn one on, we should turn it on the right side. So let's go over this note I have for that. So if x needs more set bits, we should add them on the right. At every index starting at the far right, we will check if that index is set. If not, we will set it. So here, we'll start looking on this side here. So we'll start looking here. Now, this bit is set, so we can't do anything. So then we move back 1. And now we notice that this bit is not set. If it's not set, we'll set it. So then we would change this to a 1. And then, well, we would actually be done here because we only need 5 bits. And notice how x has 5 bits at this point. And then when you XORed A with x, we would get we would just get this. There would be zeros in front that are not necessary for demonstrating or presenting. So we would get this. Okay, so I think we can kind of implement that part. So let's do that. So one question you'd be asking is, how are we going to figure out the number of set bits? Well, luckily Python comes with a helpful method for that. So let's set a and b equal to a dot bit count and b dot bit count. Okay, so that's the method Python makes available for this. And remember, what we'll be doing is we'll start off x with setting it equal to a, and then we'll modify it as needed. So let's do that here. So we can just set x initially to a. Okay. And what we can do though is just so we can get it out of the way is return x. We can do that. Now, let's start off with this part. So if x needs more set bits, so how do we know if x needs more set bits? Well, we can say, well, remember initially x has the same number of bits as a does. So remember x equals a, and then a is the number of set bits. So we can say while a has less bits than b. So what do? We should add bits on the right. So we need to check on the right side if the bit is set. So let's do that. How can we check if this bit is set? So what we'll do is we'll say we'll AND it. We'll start off with this here. We'll say if a ANDed with this guy, we'll AND it with 1 on the very, very right. And if this is not set, we'll set it. But in this case, notice how they're set, so it wouldn't yield anything of value. However, when we AND it at this index here, this 0 here, 0 and 1 is 0, so we'll set it. So let's do that. So we'll say, okay, so we'll say if a is less, while a is less than b. Now let's check if that bit is set there. So we'll say if, now we'll do something like, sorry, give me a moment. Sorry, we can say if 1 I and, sorry, yeah, that's right, and a. Now, if this bit is not set, so the way we check if it's not set, it equals 0. So if it equals 0, then we'll set it. So how do we do that? So we just say x, then we use the x, so it's not set currently, so we'll do that with that particular value, with this value here. We want that. Okay, and then we'll increment a, because we've just added another set bit there, so we can adjust it. And now we'll need to know what this I is, so we'll initialize this I to 0. And let me go over what that means. I think I missed a parenthesis here. I don't think I need, I'll just put it here. Okay, so let's go over what this does. So initially, well, let's print this out. So what does this do here? So this is 1 here, and it says, this is saying 1, move it over 0 to the left. So that means it doesn't move at all. And what we'll do is we'll kind of just print out some other ones. So we'll say we'll shift it over once, shift over twice, and 3 times, just so we get a look at it. So that's what we're doing. We're moving along. We're moving along to the left. And let's just print it out. And I think this is okay. I'm just going to print it out. And we're not done yet, but I just wanted to understand what's going on here. So here we had 1 and we shifted it over nothing, so it's still 1. But here we shifted it over 1, so this becomes 1, 0, which is 2 in binary. And actually, let me do something here as well. How about that? Bin of this 2. How about that? Maybe so we get a better idea. How about that? Sorry, give me a second here. 2, 3, 3, 2. All right, let's demonstrate it again. So we shifted over 1, and it's sorry, this first one we shifted over nothing, so it's 0. That's why it stays 1. But here we shifted over one like space or one like index, and so we get 2, 4, and 8, and this is what it would look like in binary. So, and essentially though, we're going to end this value, and we'll check if this is turned on for every index of. Remember, we want to do that here, so we're doing that here. Like for each of these, we're checking if this is on or off, and we use the AND operator. This, so AND means and 1. So if you 1 AND with 1 is, if it's 1, it means it's turned on. So the only way we know we're guaranteed if 1 and 1, if they're both turned on with an AND, that's the only way we get a true value. Okay, so let's go back. Okay, so I've demonstrated this part here. And now let's do the same thing when A is greater than B. So let's go back here. So while I is greater than B. So what happens when A is greater than B? So that means A has more set bits than B. So let's maybe adjust this. So A has 4 bits set, and B has 3 set bits. Let's put back A to its original value. So remember, we initialized X to be A, and we're going to adjust it depending on what B is. Sorry, we're going to adjust it depending on how many set bits there are in B. So we need to adjust X so that X only has 3 set bits. So we need to remove a bit. Now the question is, what bit do we remove? So if we remove this one though, that's not good, because it wouldn't help us, because when we XOR X with A, notice how we XOR 1 with 0, that's 1. And then everything else would be 0 because they're the same. So we would get something like that. Let me see, 2, 4, 5, one more. And this is what, 64? So if we had gone the other way, suppose we had removed this set bit here. Well, then when we XOR this, we get this, which is only 1. So remember, the goal is to find a value X such that X XORed with A is minimal. So we kind of need to do the same thing that we did here. So notice I have another paragraph here. So if X needs less set bits, we should remove them from the far right. At every index starting at the far right, we will check if the index is set. If it is set, we will remove it, or maybe unset it is better. Unset it. Okay, let's do that. Okay. So we're kind of going to use the same thing here. So first we're going to start off at the 0 one, so I is 0, and then we're going to end it with A. But now we don't want it to be 0. We want to check if it is set. Remember, if it is set, we will unset it. So this is what we're looking for. So when this equals 0, it means it's not set. And this will give you a value greater than 0 if it is set. If it is set, let's unset it. So we'll say X or equals 1 I. And now that we've unset it, we can reduce A, because A has 1 less bit set. And then we need to increment our I. Okay. So let's test it locally with these tests. Okay, let's submit it. Okay, looks very good. Very, very good. Okay, so now I'm gonna implement the solution in C++. I think it's good for developers to know more than one language, um, because it helps us become better developers, and it helps us think differently as well. So let's get started. If you only wanted to see the Python 3 video, then by all means, feel free to carry on. All right, let's move on to C++. Oh, yes. As I mentioned, I already solved it, but I didn't record it, so I'll just start it over again. Okay, so here we go. Where are we at? Okay, so as I mentioned before, we want to know the number of bits in each of num1 and num2. So, well, how do we do that? So C++ has their own like version of like a bit count available in Python, so we can use that here. So we can say int a, and I'm going to change these really quickly to a and b. Let me just get this out of the way and make this a little bigger. A little bigger. All right, okay, cool. So int a will be, and C++ has this built-in pop count, and then we'll pass in a. So this will give us the number of set bits for a, and then we can do the same thing for b. Built-in pop count b. Okay, and then like last time, we're going to initialize x to be what a is initially, and then we'll modify it as needed. So like before, let's check if a is greater than b. So int I equals 0. So while a is greater than b, so what does this mean? So this means a has too many set bits, so we should remove. Really though, in a way, this really means x has too many set bits, but it's a small subtle distinction. So remember though, initially x is and a are like very, very similar. Notice how, because we set x to be a. Okay, so let's do it. So if one right or left shifted I times and a is greater than 0, so this means that the bit at 0 is set at a if it's greater than 0. If it is, remember we need to remove it. So let's remove it here. So we say x XOR or equal 1, and we'll remove that bit there from that. We will unset the bit at that location. And now, since we removed a bit, we can decrement I. And we still need to move forward with I. We need to increment it until a and b are equal. Okay. Now we need to do the same thing for when a is less than b. So let's do that. So let's maybe just copy this down. Actually, no, let's not do it. So I don't need to declare I again, but I do need to reset it. Now, while a is less than b, in this case, what does this mean? This means that x needs more bits. So we will set bits starting at right. Yeah, that's fine. So what do we do here? So kind of like the same thing. So we say if 1, so 1 shifted I and a. Now it needs more bits. So we look for bits that are not set. So when a bit is not set, it's equal to 0. So this means when we find this, this bit is not set at the I location. So we can set it. So we can say x XOR equals x XORed with 1 I. And now that means we added a set bit, so we need to increment a. And then we can increment I. Okay, and then we can return x. So let me go over something here. I could have consolidated these two methods, but I think it's what's the word? It's not quite right, because even though there's a lot of duplicate code, there's some things that don't change in the code, meaning this. So I could have done a while loop and just put while a is greater than b. I could have put it inside the loop, something like this here, and then added this here as well, maybe something like this. And then this is for if a is less than b, and something like this. We could have done this, but what I don't like is that you'd be, every time you run this loop, this probably wouldn't be there, but every time you ran this loop, you would check this a greater than b, and then you would check this also. My point is, you'd be checking something that doesn't change. So my point is, if this is false, it'll always be false until like it's not. So meaning it'll always be false, because suppose a is like 10 and b is 100. So we'll always keep doing this, but we'll also be checking this. But we know it's not true. It won't change. The best it will do is it'll become equal. Sorry, maybe that wasn't the best value. Maybe a is a is 100 and b is 10. Yeah, sorry. So anyways, I just find it a little bit cleaner if we separate them. I just think it's a little bit better, a little bit cleaner. Yes, and notice though, once this is true, meaning this loop will stop when a equals b. That means this will not execute, because we're only checking if a is less than b. So we don't need to worry about both loops taking place. Probably better would have been to make like a separate method for it. But since this is not too complicated, we can do it in this single method here. So I think we're okay. And well, let's check it now. Let's submit it. Okay, looks good locally. All right, looks very good. Okay, if you found this video helpful or educational, please consider liking or subscribing. Other than that, have a wonderful day. Take care of yourself. Cheers.